All right, what's up, everyone? Welcome to week 55 of Chill Kernel Hacking for Fun. This week, we are continuing with Lab 5 from the MIT course. And we are continuing with exercise 8 specifically. So in the last couple streams, I've made progress through this file system lab. We've gotten our basic file system working, and now it's time to make use of the file system to implement kind of like an exec system call or a spawn system call, which allows us to take a program on disk and load it and run it. So that's what we're gonna keep doing today. I'm going to do a quick test as usual to make sure that chat widget is working. And anything else? I think we're good to get started. So yeah, for anyone joining the stream, actually I will I've moved a bit forward actually since last time. And so last week I recorded week 53, and I kind of buggily did this. I actually pre-recorded a stream where I fixed that, and that will be released next week since I'm away. So that will be week 54. But today is week 55. And we're working on exercise 8. So, yes. What are we doing in exercise 8? Sharing library state across fork and spawn. I have no idea what this means, so I'll need a bit to read about this. Okay, so Unix file descriptors are a general notion that encompasses pipes, console I/O, blah, blah, blah. In JAWS, each of these device types is a corresponding struct dev with pointers, functions. So it's kind of like an interface. libfd.c implements the general Unix-like file descriptor interface on top of this. So making use of the struct dev interface, fd.c is implemented in terms of this. Yo, what's up, Canada honk? Hey, yo, yourself. Hope you're doing well. Thanks for joining the stream. File descriptors. So we have this device interface. FD is coded in terms of that interface. Each struct FD indicates its device type, and most of the functions simply dispatch to the appropriate, or dispatch to the functions in the appropriate struct dev. Interesting. fd.c maintains the file descriptor table region. Still hacking on a project too. Nice. Super cool. Do you want to share what project you're working on? Kind of curious. Is it like a OS kind of thing or something else? fd.c maintains the file descriptor table in each application's environment address space, starting at fd table. So each process has a file descriptor table. I think it's even accessible from user space, potentially. This area reserves a page's worth of address space for each of the up to max FD 32 file descriptors the application can have open at once. Why is that so low? Okay, at any given time, a file descriptor table page is mapped if and only if the corresponding file descriptor is in use. Each file descriptor has an optional data page. in the region starting at file data, which devices can use if they choose. Okay, interesting. We would like to share file descriptor state across fork and spawn. But file descriptor state is kept in user space memory. So right now on fork, the memory is marked copy on write. So the state will be duplicated rather than shared. I see, okay. Kenda Honky working on a compiler. Crazy, that's very cool. Very, very cool. Hey Adam, which kernel are we hacking? We are hacking on this kernel from this MIT operating systems course. And I'm doing a bit of kernel development on it in the area of process execution and exec system call. Yeah, this OS is kind of like a microkernel actually, so it's kind of exotic. A lot of stuff happens in user space, like fork. The fork system call happens in user space. Yeah. And yeah, we're dealing with that now. So basically we have processes and they can open files and have file descriptors. And currently in the OS, if you spawn a new process, it will not share any of the file descriptors. Okay, yeah. Right now in fork, memory will be marked copy on write. So yeah, anyway, but this is interesting. The file descriptor state is kept in user space memory. So this is kind of like that microkernel thing, where yeah, some of the state that you might normally expect to be in kernel space is actually not. And it's sort of in this like user space part of the operating system. It's like not an application. It's just part of the operating system that lives in user space basically. Such as this file descriptor state, I guess this file descriptor table, stuff like this. Okay. So basically right now, I guess, so on fork specifically, the memory is marked copy on write. So this is going to be duplicated when you use it. So environments won't be able to seek in files they didn't open themselves, and pipes won't work. Interesting. So yeah, there's this file descriptor state, which I am actually not that familiar with. It might be a good time to take a look at what file descriptor state even means. Give me one sec. So we have, yeah, I'm not that familiar with a lot of these structures. This is the device interface. For example, writing to files on disk, or it would be one type of implementation of this interface. Another one would be console IO, I suppose. Like stood out, or like the general, yeah, like stood out, stood in, stuff like this, I think. But anyway, file descriptor state is stuff like this. It's actually not that much state. It is basically, for example, an offset is one of the main pieces of in-memory state associated with the file descriptor. I guess the mode is also part of the state. So anyway, we have this state, but yeah, we want it to be shared, I suppose, between a parent and a child. Although I'm still kind of ramping up on that. Like, and this sentence in particular, environments won't be able to seek in files they didn't open themselves. Why not? So they're going to have a separate copy, of their file descriptor state, but that will have a seek field. So, and pipes won't work. Okay, I don't even really know how pipes work in this OS anyway, so I don't quite understand that. On spawn, the memory will be left behind, not copied at all. And so yeah, so basically it's saying there's two problems. There's a set of problems that happen with fork, and separately, when you spawn a process, all the file descriptors are wiped out currently, so there's no sharing possible. But we would like to. Let me create a new workspace for today. So this is 55. Working on my own profiler to optimize compiler's output to meet our needs. Nice. Own profiler. That's cool. What kind of profiler are we talking about? Like, does it, like instrument the program, or does it just analyze the program for instructions or something like this? So you profile the running program, presumably. Okay, cool. What's up, Andrew? Hack the planet. Exactly. That's the goal. Hack the planet, or at least implement an operating system. Yeah. Okay. So basically, there's a bunch of problems. Fork won't, like currently, fork won't work with file descriptors, and also they'll get left behind with spawn. So I guess we want to make some changes. We will change fork to know that certain regions of memory are used by the library operating system and should always be shared. Right, so there's some special parts of the user space. Operate the planet. Exactly, operate the planet. More love for our kernel devs. Whoop whoop. Need. Nice, appreciate that, Andrew. Yeah. I agree. Need more love for our kernel devs. Yeah. Okay, so basically here's the idea. I will try to sketch this out. This is our, how do I make this thicker? This is our user space process memory, and we have, there's just like certain chunks of it that just contain important data, like file descriptor state. And when we spawn a process and make a child process, we actually want that to be shared. So maybe I'll move this here. We want that to be shared between the two. Currently that's not happening. Oops. Wow. Currently we get separate copies. And so when we fork a process, we want to basically mark that certain regions do not participate in copy on write. I think the general flow of forking is we have a process state and we enumerate the page tables of the process. And for every mapping in the process, we kind of replicate, well, we make like a replicated mapping in the child and then mark everything as read-only. But we also store a special bit in the page tables. So we can tell. Let's look at the code again. I forget how this works. Fork system call. Okay. And remember, this happens in user space. So the program creates basically a blank process, and populate mappings in child is the important function. This is optimized. So then here we're enumerating all the page tables to find mapped pages in the process. So if there is no page directory entry, we totally skip that. But if there is a valid page directory entry, we then go one level deeper. And for every page table entry within that page directory, we look at the page table, and if it's present, then we basically do paste it. There's this one current exception where a direct copy happens, but usually this dupe page thing is called. And dupe page maps the page into the child. And then unmaps, and then removes the writable flag in the parent process. And in this case, when it's a writable page, we mark it not writable, but we also set a cow bit in the page table. And this is used later when there's a page fault on a page. So then the parent and child are running, and one of them tries to write to some memory, which triggers a page fault. Okay, this is kind of weird. It's a write. Okay, this is just kind of like an assertion, basically. If there's a write, if the page fault is from a write, it should be writing into a cow page. Basically, we should not have write page faults that don't correspond to cow pages. All right, palm tree break, 20 seconds to stand up and stretch and get some water and whatever. Okay, so this is an assertion. The real interesting, actually I guess that's it. We don't actually check, we use this for asserting, but that's basically it. Or am I wrong about that? So we're using it again in some checks. No breaks allowed. No breaks allowed. Yeah. Found bottom one time to write Cindy version of it. Nice. Okay, anyway, I was going kind of deep into this. Let's get back. So we're just going to tag, right? So we want the fork to know that fork should be able to know that certain regions of memory should always be shared and should not participate in cow. And we'll do this with a bit. Apparently it's this share bit. if that bit is set, the PTE should be copied directly from parent to child in fork and spawn. Okay, that's pretty important. So unlike usual, where when we do cow, we share the page, but we mark it all as not writable, and we mark the cow bit. In this case, we're not going to do that. If we see that there's a PTE share bit, we are just going to directly share them, and that's it. We're not going to make it not writable and stuff like this. All right, let's code. Exercise 8, change due page and lib fork to follow the new convention. Let's do that. We were even looking pretty close. So just as a reminder for context, the caller is right here. This is the code that runs for every page table entry that is present, basically, in the parent process, which means we need to take some action on it. And the action can be one of a few things. If it's a simple read-only page, it's very simple. We just map it also read-only in the child, and that's super simple. However, if it's writable, or if it has the cow, or if it was previously cowed by another parent, then we need to participate in cow. So yeah, what's up, Joy? Why do you recommend any ebook or resource study kernel hacking? I got you. I'm gonna link you to my resources page, which has quite a few links to like books and stuff about this, also courses, but really the quick answer is my top recommendation is this website called spawn.college, which is one of the best like resource websites that I've seen with challenges and educational content about how to get into low-level programming, low-level hacking, also from a security perspective. I haven't done it personally, but I've done a lot of similar exercises in the past, and that one looks really nice. And I know some of the people that made it, and they're pretty elite. So Andrew, when I dev new stuff, I end up going on research tangent. Do you seem so focused? How do you pace yourself? Keep on task. Notes. I do a lot of research tangents also, but like, I mean, right now I have some very specific tasks that I'm trying to do. I'm specifically just trying to complete these exercises. And so I'm trying my best to not go on crazy tangents, but in my personal time when I'm not streaming and stuff and I'm just learning about computers, I go on really deep, wild tangents. But if you want to, I don't think there's a problem with that, but if you want to not do that, then yeah, I think, maybe just setting a bit of an intention for yourself, with your research session and noticing when you're kind of going on a deep dive, and then making kind of like a note or a bookmark to save that for later, rather than just going kind of depth first and diving right in. So I think that's what I have on my thoughts on that question. Okay, change this. If the page table entry has the share bit, just copy the mapping. You should use pt syscall not hex fff to mask out the relevant bits. FFF picks up the accessed and dirty bits as well. Okay, let's just do that one. So I think we can do this kind of early. Handle shared pages. If PTE and PT share then we just want to map the page from our process to their process with basically the same permissions, but clearing out a couple special bits And so we're basically preserving all of like the entire page table entry. Well, we're preserving 4 bits. Well, actually, no, we're preserving the important bits, like the user space or not bit, write or not bit, present, and available is a bit of a broader mask for other bits that I guess aren't in use or aren't interpreted. And so the key point there is that we're preserving these bits, but we're clearing out a lot of other bits. Like we're clearing out the dirty bit, access bit, I don't know, some other stuff here. So yeah. Oh, hey Jose, hello from Venezuela, welcome. That's awesome. That's very cool. How are you doing, Jose? Hope you're having a nice day. Yeah, if anyone's like working on any cool projects, feel free to post about them. Always curious what people are working on. Okay, so that's my kind of first take on how to handle this. And actually what I want to do, in this case, my intention is just to stop execution of the program. Of the function. I don't really want to keep going and executing these things actually. For example, if it's shared, I just want to do this and then leave. I don't want to accidentally like do another mapping, so I'm going to success. I'm going to add a go to success. And I think maybe I could also just do this here. What's up, Creeper? He came from X. Nice. Oh, hi, Mark. Good reference. That happens to me at least once a day. So, yeah, if you're curious about the life of a Mark, that's what it's like. Yeah, so I think that's the general pattern I'm going to use here. If the shared bit exists, we just map it over, clear out some bits, and that's it. Yo, Wilson, what's up? Big ups, my friend. Awesome project you were working on. Thank you very much, and thanks for coming back. Yeah, appreciate you being here again. Hope you're having a nice Sunday. What's up, Andrew? Question about goto. Why goto? Isn't it bad practice unless we're doing ASM jumps? I'm confused. I think gotos get a bad reputation, but I think they have specific use cases where they actually lead to the best code, and that use case is for error handling. This is a very common pattern in C programming where you go to the end of the function where you have some different returns. Because the alternative is I could copy and paste like some return zeros here, but if I don't want to do that and want to consolidate all of that, it's actually not really a bad idea to use a goto and just jump directly to the exit condition. So yeah, a lot of people say goto should never be used, and I think they're mostly right except for this use case. Does it build? Oops. It does build. Okay. Likewise, implement copy shared pages in spawn.c. Let's check that out. Okay, so basically what I just did is I handled the first part of this paragraph. So this is saying basically there's a problem. The problem is file descriptor state is file descriptor state will not be shared properly at the moment in fork and in spawn because of some reasons. I just fixed the first one of these. I fixed the problem with fork. Although actually, I fixed part of it, but actually we need to set PTE share somewhere also. And I don't know if it's already doing that. It is. Interesting. So we just fixed the code that runs in fork. And this code looks to see if the shared bit was set and handles things properly, but someone needs to be sharing, like marking these pages as shared in the first place. And that's what we're seeing here. And I didn't write this code. This was pre-provided by the course. So good to know that there is someone out there that is marking these as shared. Okay. Okay. Yeah, go to use to jump to random locations isn't good. Yeah, it can get ugly quickly and produce very hard to read code if you're not careful. Maybe there are some use cases where it actually leads to the best code with the least duplication and stuff, but yeah, I don't think anyone would encourage you to just have like random go-tos like all over the place. That would create really hard to read code. Okay. Copy shared pages. So this is the second, this is solving the second problem. The first was in fork, the second is in spawn. Let's check out spawn. So spawn is our library call for basically executing a new program, loading it from disk and executing a new program. What we need to do, okay, copy shared pages. This is also new to me. Shared pages. And I need to implement this, apparently. Okay, what is this function? Copy shared library state. Do you also stream to Twitch? I don't right now, but I've been thinking about it. Mostly I just didn't really have a setup for doing multi-streaming, and I never figured that out. But I've been curious about it, yeah. If anyone has any tips on how to do that, I would be very interested, because I'm still like a little bit of a noob. Like I know how to stream to YouTube because I've been doing that for a while, but yeah, like multi-streaming and stuff like that, a little bit less sure about. Copy shared pages. So zooming out for 1 second, what is this doing? So we're in the spawn function. User space processes can call this function to create a new process on the system. They need to pass a file system path and some arguments to pass to that program. And then we do a lot of stuff. Although it actually doesn't look like so much, but first we open the file on disk and read the header. And just kind of validate the header. Magic looks correct. And then this is a little bit slightly similar to the fork code. In fork, we're a parent process. We use exofork to create a blank new process and then basically populate it with like all of our stuff in the parent process. The difference in spawn, we still create a blank new process, but instead of populating it with all the contents of our current process, we populate it with the memory state of the binary that was specified. So yeah, and we can just quickly step through that. So exofork creates the blank process. Then there's a couple high-level things to do. There's basically setting up a bit of register state, which involves this thing called the trap frame. Second thing, setting up the stack state of the child. Third thing, loading the program's segments into memory, like the code and data, stuff like this. And now apparently we're doing a fourth thing, which is copying the shared library state. And that's going to be very similar to what we did over here, I think. Let's see if they have any tips on how to do this. But my guess is going to be we need to do something like iterate over the page tables, look for any mappings, any page table entries that have the share bit, and directly copy them. So I think it'll be quite similar code to over here, actually. Let's just quickly check this thing. Implement, it should loop through all page table entries in the current process, just like fork did, copying any page mappings that have the PTE share bit set into the current process. Okay. So I'm going to just try to do this, and I'm going to copy and paste a bit of code from the other function. This is, I think, a slightly optimized. This is my slightly optimized version of the routine. But yeah. Yo, what's up, Jesse? Can't say I did, but I'm subscribing. Thank you very much for the sub. Appreciate that. And I'll see you another time. Have a nice day. And also, what's up, John? Nice to see you. Our user binary is statically linked. Yes. There is no dynamic linking. Yeah, I mean, that's an interesting question, actually, but like just like straight up, yeah, no, there's no dynamic linking. There is like sharing of memory between processes, but that just happens via the normal like fork, the way you can share data with copy on write, basically. Yeah, dynamic linking is quite far in the future, I would say. All right. So copy shared pages. So what's the goal here? Iterate through every page table entry and also, but how does this work? Okay. It's been a while since I wrote this code. So going through every page directory from 0 to, okay, that macro is kind of crazy, but utop, right. Okay, let me just bring up the memory layout to explain how this works. But before I do that, quick 20-second break to stand up and stretch and get some water, whatever you want to do. Right, so here's what the memory layout of user space looks like. We're on 32 bits, so it goes from 0 to 4 gigabytes. User space has the bottom part of memory up until this thing called utop. I see the custom hoodie finally made it to the stream. Yeah, let me just show this off to the camera quickly. Yeah, I don't know if you could see this very well. This is like a custom hoodie I made. It has this diagram of the x86 64 like paging mode transition state. This is a real diagram. Yeah, quick aside. Thanks for pointing that out, John. Quick aside for how do I find a file? Full Intel manual. Quick aside. So look at my favorite diagram ever. Intel manual. And if we go to operation. Wait, what diagram is this? This is diagram 4, figure 4.1. I think we're getting close. Here we go. Check this out. All right, so take a look. So here is the diagram. This is a real diagram, and I basically have a version of this on my hoodie that is just kind of like a cooler version of it. So yeah, pretty cool. Let me know if you want a hoodie that looks like this, and maybe we can make that happen. Anyway, so we're trying to iterate through all of the page table entries that belong to user space, and the way we can do this is start from 0 until the top of user space memory, which starts at this thing called utop, which is hard-coded, but that's just the way it works at the moment. So basically, from 0 to utop. And then we get the page directory entry, and if it's not present, we continue. Otherwise, we iterate through all of the page table entries from 0 to 1024. And so page dir index, right? And so based on the page dir index, we can get the start virtual address of this range. And then it's a little bit, maybe a bit convoluted, but then we iterate through every page. Yes, we iterate through every page table entry. Yo, what's up, Afnan? You're late again. It's all right though. All good. Good to see you again. Also, what's up, digitalized? Thank you very much for the sick hoodie comment. Yeah, hope you're all doing well. Yeah, so we find a page directory that's mapped. We compute its starting virtual address. And then for every single page table entry within it, we compute the virtual address. So it's going to be the base plus that times page size. So each of these 1024 things controls a page size amount of space. We map that back down to a page number, which is a bit convoluted, but that's just how you need to use this interface. And we can look up the page table index. And finally, we can do a check. So if it's a present page table and it's PTE shared, what's this constant? Isn't it PTE shared? Share. Okay. If it's present and PTE share, then we share. Then we go and basically do something very similar to what we have up here. Yeah. We want to right. There's no fail yet. What does this return? An int. Okay, I'll make my own fail. Return enval. I don't really know what to return. I'll just do enval. It's error. Env ID child. So it's gonna be child, and what is adder? Adder is page v adder. Page v adder. I always forget what the type is. It takes an actual void star. So we will need to cast this. So something. Why is this? Am I missing Am I missing? I don't think I'm missing a parentheses, am I? So child adder. Right, so what this does is a bit of a weird function that they have here, but using this function, you can specify a source and a destination. The source is the basically process ID and a virtual address, and the destination is the process ID of the child and a destination virtual address in the child. And you can basically share a page of memory share the page of memory that's currently mapped at page vadder to, and make it appear at this location in the child with the following permissions. And in this case, PTE is correct. So why doesn't this compile? Okay. Am I missing a parentheses or something? That's stupid. Okay, that did not help. What? Is it the yellow thing? Or maybe I cannot declare an integer like that. Or also maybe my return. But no, I think now this is like all super weird. Okay, this is very stupid. I don't need error though, so what am I doing? I don't need to assign this. Okay. There we go. Make. You cannot declare a variable inside the if statement. Average, what's up, average deviant testing enjoyer? Interesting. I definitely do this in C++, and I could have sworn you can do it. I could have sworn you can do that, but maybe I am misremembering. Okay, we are compiling. So basically that's my first cut at this. It's possible that there's a simpler way to do this without first looping over the page directories and then looping over the pages, but I think it would be kind of slow otherwise. Otherwise, you would just be doing a lot of blind, like you would just be like checking all sorts of pages for no reason. Because if the page directory is not mapped, you know you can skip those 1024 entries. So I think this is a decent way to go about it. Okay, so now what do I do? Run test PTE share, check that your code is behaving properly. You should see lines that say fork handles PTE share right and spawn handles PTE share right. Let's do that. Okay. Moment of truth. Moment of truth. I think that did not work. Wait, no, it did work. Fork handles PTE share right. Spawn handles PTE share right. It just like weirdly hit a breakpoint for some reason. Let's take a look at this program, test PTE share.c. This is the program I was running, and I actually have never seen it before. What does it do? It if argc is not 0, so if you pass an argument, it hits child of spawn, which stir copies like a message. Okay, that's weird. I guess it like executes itself or something like that. So first it allocates some random like memory with the share bit actually, and then it does a fork. And then if it's the child, it copies a message and then exits. But it's a special region that does not participate in copy on write and is just directly shared. So therefore, the parent should be able to observe this. So the parent waits on the child to exit and then observes the VA state and sees if the message is there. And if the message is there, it prints this message saying you handled it right, and it says that for me. So that's test number 1. Test number 2 is for spawn. So now that's done. But now we're still in the process, and now we spawn ourselves basically, but this time we pass an argument, and then we wait on that process. That process starts from main, and this time it sees that there's an argument, so it does the child of spawn thing, which does basically the same thing, but just copies a different message, I guess. Goodbye world, and then it exits. So it's a very, very similar test. So the parent spawns the new one, waits for it. In the meantime, the child goes and copies a message, and that should be observable to the parent, and then the parent checks whether that message was copied into the shared memory region, and it was. And then it hits the breakpoint, which is why it like alarmingly trapped right there. So that's great. That means it's working. Let's run the second test. Use make run test fd sharing to check that file descriptors are shared properly. So this first test was just testing that this PTE shared kind of like ability works in the OS, that a process can have pages marked PTE shared, and when the process forks or spawns, those specific pages are kind of handled differently, and they do not participate in copy on write and are just a simple like mutable writable shared memory. This is then building on top of that, we can test that file descriptors are shared properly, because file descriptors are just stored like in memory basically. And so we're going to mark all of that file descriptor memory with the share bit, and then that's going to mean that that file descriptor state gets shared. The big question though, I'm wondering, is how do they make sure this is thread safe? Because all that file descriptor state is mutable and shared, basically. So that's my question. How do they make sure that the shared FD state is in a thread safe way? For example, if you have these two processes that are doing stuff with files, or maybe the same file, and they get scheduled and interleaved, you could imagine that would be kind of bad. So I am kind of curious about that. I don't actually know. Let's run the test though. Moment of truth. Okay, what is it? It should say read in child succeeded and read in parent succeeded. Read in child succeeded, read in parent succeeded. So I'm gonna call that a major win. This seems to be working, and I think exercise 8 is finished. Nice. So as usual, let's go take a look at the Git history to see if there's anything to clean up or whatever. But nah, I think yeah, I mean this code probably could be improved in some ways, but I'm not really I'm not doing this ultra clean code thing right now. I'm just kind of powering through. So all right, exercise 8. Implement support in fork and spawn. Cool. So that's working pretty well. I want to take a moment to revisit a question that they posed earlier, which I didn't know the answer to. They're saying we implemented spawn rather than a Unix style exec because spawn is easier to implement from user space in exokernel fashion without special help from the kernel. Think about what you would have to do in order to implement exec in user space and be sure you understand why it's harder. Okay. I had some notes about this over here. There's also this thing which I didn't. It's a bunch of to-dos, questions that I didn't have answered. So maybe I'm just gonna think a little bit about this first question though. So let's just recap what currently happens. This is spawn, and this runs in user space, and it requires a certain amount of kernel support to do this. What is that kernel support? Oh, all right, palm tree break, be right back. What's up, PP Poo Poo 69? Thanks to you, I started learning more about kernels on OS. One of your videos came up. Now I'm learning more about kernels. Awesome. Well, glad I could help inspire a little bit. Nice username, also. Yeah, feel free to join the Discord and post updates about what you're working on and stuff. Yeah. A lot of other people that are interested in that stuff are hanging out there. Okay, what kernel support does spawn need? We need a couple things. First one, sys exofork. This is basically just creating like a blank new child. We use normal like file reading and stuff to read the file from disk. It's not that special. Map segment does some other stuff. It allocates memory in the child, basically. That's pretty much it, actually. So we need to be able to allocate and put memory into the child. Same thing with this library state. We're putting more memory into the child with this page map. And then we do two more things. We set the trap frame, which controls the register state the child will enter with, and then we mark the child as runnable. So what? So exo fork, page map, set trap frame, set runnable state. These are kind of the kernel primitives that are used in addition to like enumerating page tables with UVPT mechanism, that thing, which is not like a syscall, but is like a little bit conceptually similar. It's just data that the kernel exposes to user space, but there's no syscall involved. Okay, so what's up with exec then? Like how is exec different from this first off? So this is making a new process and loading a bunch of stuff into the new process and then marking it as runnable. Exec is different. Exec like takes over a process, right? That's the semantics of exec. Yeah, and what does that do? That just requires changing a lot. It requires completely resetting lots of state within the kernel, freeing resources. It's just a wholesale, like, kind of hollowing out of the process and putting new stuff in it. So that's my initial impression of the main difference. It's just more stuff, basically. Without special help from the kernel. Yeah, that's my like guess, basically. So to implement exec, I think we would need to expose a lot more system calls for changing all sorts of random stuff in order to really do it from user space, right? We can obviously just implement it in kernel space and just access all the stuff we need to. That's, that's like table stakes. That's like normal, but the question is specifically, how do you implement exec in this like microkernel kind of thing where you're not in the kernel? And I think basically the answer is that you just need to expose a lot more syscalls to just do a lot more stuff, which sounds quite cumbersome. And I don't know, maybe even defeats the point of being a microkernel. Maybe not. Maybe there's still enough core logic that can live in user space to justify needing to add all these extra syscalls. But that is generally what I'm thinking. So with exofork, with spawn, we need like 4 syscalls basically, but we're just creating a new process and then kind of populating it. With exec, we need to actually release a lot of resources. We don't release resources with spawn. So we just can make new stuff. Okay, this is harder from exokernel because it requires releasing resources and I don't know, manipulating potentially all parts of process state as opposed to creating a new process and filling it in. Something like that. Okay, moving on. What was this other question? Be sure you understand why you can't use read map here. Oops. Let me read map. Okay. So this, what is it? This is part of the ELF loading code. And it's talking about, okay, if ELF segments flags have writable, then the segment contains read-write data and BSS. Quickly, I want to just check on that actually, because I was a little bit interested in why the BSS like it makes it sound like the BSS has the right flag set. Like BSS data is writable, but I guess that just gives me pause for a second. Like, where's BSS in the kernel? BSS is in section 4, which gets mapped into segment 1, which is writable. BSS should be writable conventionally. Yeah, I mean, that like makes sense. BSS is what uninitialized data. Yeah, I mean, it probably would not make sense for BSS to be not writable, because then it would just be zeros. So what happens if you want to allocate just a big, like a lot of constant zeros? I guess that goes into the read-only data. So that will be initialized at, like, the compiler knows that is set to 0, so it can go into the read-only data, I suppose. But then if you just declare a random global variable, probably the intention is to write to it. Yeah. I think I understand that, but that's like a bit of a basic thing, but it's always funny to see how just like doing stuff makes you kind of question your knowledge. Yeah, what's up, Sacrificial Lamb 22? Have an interest in coding program. Is it too late to learn it with all new AI stuff? I would say no. I mean, AI will change programming, but it's not like this kind of thing hasn't happened before. Like when compilers were invented, and that they didn't like completely, eliminate the need to do programming. I mean, AI is different, but I would still encourage you to get into it. I think technology is not going away, and so there's still value in understanding how computers work, even if you use AI. Okay. Then insert the page mapping into the child. Look at init stack for inspiration. Okay. Only the first bytes of the file are actually loaded. You must clear the rest to 0. comment is super hard to read. What? That page. Then insert the page mapping into the child. Okay, init static for inspiration. So first of all, where does this happen? I guess this happens in map. Segment. Or maybe not. So basically here's where we go through the ELF headers. We check if it's writable, and if so, we just attached the W permission onto it, and we call map segment, which is given a child, a lot of things actually. I don't totally understand all this. A child, virtual address, mem size, file descriptor, file size. So the destination virtual address of where this is eventually going to go, which is used here when we map it in, although I is kind of interesting. File size, 30 plus transitioned into operating system development. Definitely not too late. Anyway, it won't kill your job, it just changes it. Yeah, totally agree. Totally agree. Okay, this is like super in the weeds, and I don't want to stay here for too long, but just about this question, be sure you understand why you can't use read map here. So zooming out one second. So what are we doing here? We're taking an ELF file and loading it into memory in the child process. And we're looking at the load commands or the load segments to determine the different chunks of the file to load, like where to load them and with what permissions to load them with. And the general flow of this is interesting. Yeah. The general flow for read-write segments is to first allocate a page, copy the data into that page. That's what it says right here. Make sure you memset anything necessary based off of the difference between the mem size and the file size. So the file size might go to a certain length, but there might be additional space after that point. So the mem size is greater than the file size, and you need to zero out that remaining space. And then after you've set that up in the kind of temporary allocation, you then move that into the child where it needs to go. And saying you don't use read map here. So what is up with read map? So read map is this thing it mentions here. So if the ELF flags do not include the writable thing, that means it's read-only data. Then it says use read map to return the contents of this segment and map the pages it returns directly into the child. So multiple instances will be shared. Be sure to map the program text read-only in the child. I think that actually, wait a sec. So I didn't write this code. So we should see some read map calls somewhere. Am I right? Okay, I don't actually see them doing this, which is very confusing. Interesting. All right, John. Have a nice one. See you later. Okay, so they're saying this read map thing should be used. It's actually not at the moment. There wasn't an exercise to make that happen yet. But basically, read map returns a pointer to the data in block rather than copying the data into another buffer. Let's take a look at read map. How do I find read map? There is no read map. What is going on? This is so, oops. Okay, add read map. Okay, apparently that was just a massive troll from the developers of this OS. They mentioned this thing which literally doesn't exist. So maybe that's a future exercise, I don't know. That wasted a lot of time, okay. Okay. But read map is a function that directly returns a pointer to the block cache, something like that. It avoids an extra copy and also automatically shares data, something like this. That's okay for unwritable mappings, but for writable ones we need to separately make a copy. Something like that. All right, what's next? So basically, yeah, that's that. Let's move on. The keyboard interface. Let me, okay, I already committed? Yeah, nice. Let's move on. Out of curiosity, are you doing the lab of 6.18.10 or what are you currently working on? Here is the lab that I'm working on. It's not, I don't know, actually I'm not familiar with that 18.10 one. This one is 8.28, which is a bit older, but it's when they used x86 for the OS course. By the way, that's pretty cool that you transitioned into operating system development. I might be interested in doing the same thing because I don't do this in my day job. I'll be pretty curious to hear, yeah, like what you're up to in that area and if you're like working professionally in it or something like that. Okay, for the shell to work, we need a way to type at it. So I guess that's where we're going. Ultimately, we're moving towards implementing like a full shell, I guess. All right, 20-second break, be right back. Yeah, we're moving towards implementing a full shell, which require, like, to implement the shell, we'll need to have the spawn system call to execute new processes. I guess pipes should work or something like that. But okay, this is saying, okay, we need to type at the shell. Kima has been displaying output to the CGA display and the serial port, which I have mostly been using the serial port this entire time. I don't use the display. Like, here is the display, which I never use. I always just use the serial port because it's way, I can just do it in my terminal. But whatever. So far we've only taken input while in the kernel monitor, over the console, or over the serial port, I suppose. In Kimu, input typed in the graphical window appears as input from the keyboard to JAWS, while input typed in the console appears as characters on the serial port. And that's what I've been using so far. Yeah, console.c already contains the keyboard and serial drivers that have been used by the kernel monitor since lab 1. But now you need to attach these to the rest of the system. So it has the drivers already, okay. But now, okay, in your kernel trap.c called interrupt to handle this specific interrupt. Okay, let's check out some interrupt handling. Always an exciting day when we get to do some interrupt handling. KeyBD, okay. Handle keyboard and serial interrupts. So here's, I think, the general pattern we use. If trap number equals, RQ offset plus RQ keyboard. Keyboard interrupt, which is also new to me. What does serial interrupt? That's also interesting. Doesn't appear used. Do I need to call both? Oh, I see. So it's just okay. Nice work. Junior embedded Linux developer on a modified real-time operating system. Cool. Currently just implementing smaller features like system resource limiting for processes, etc. Okay, nice, cool. That sounds pretty interesting. On a modified real-time operating system. But it sounds like also Linux is related to your work too. Nice, that's pretty cool. Okay, here's my... We've implemented the console input-output file type here. Keyboard interrupt and serial interrupt fill a buffer with the recently read input while the console file type drains the buffer. The console file type is used for std.in, std.io by default unless the user redirects them. Okay, test keyboard, type a few lines. Does this work? Hello. Okay, I think that did not work. Type a line. Hardware trap. What's up, Ray? Ayanami. Are you on Windows? I'm not on Windows. I'm on Mac OS right now. Yeah. I think that did not work. Let me try that one more time. There we go. Type a line. H. Do you own a Windows machine? I do not own a Windows machine, actually. Do you? Okay. So the Octo project as the base distro and patched it with Xenomai. Ah, I see, got you, cool. Nice. Co-kernel approach for real-time domain and Linux domain. Okay, nice, cool. I have a bit of experience with the Octo also. Interesting, sounds pretty cool. Sounds like some Linux kernel hacking. All right, so this is not working. This is not working. Apparently, I type anything. Oh, wait a sec, whoa. Actually, did that work? No, I still don't think that. I'm typing stuff in here, but I don't. I think that always worked in the kernel monitor. May I ask which Mac are you? I own a Windows box. Win 11 is not really good. I am running on a pretty new Mac. It's like a MacBook Pro. Like M2 MacBook Pro or something like that. It's pretty, like, I got it last year, I think. Yeah, I'm pretty happy with it. Yeah, it was expensive, but I think it's worth it. Windows U62 says Windows kernel exploitation is far more interesting in my opinion. Interesting. That is something I know nothing about. Interesting in what way? I actually know not like very little about kernel exploitation. And the little I do know, it's about Linux. So Baranese, hello, bang. Hello, bang. What is going on? Why is... Like, I had a hardware interrupt and it, like, killed the process. Did this work? Or maybe it didn't work. Do you have a computer science degree? Kind of. I have a computer engineering degree. So I did study a bit of computer science, but it wasn't really... there's a lot of missing gaps in my computer science knowledge, I would say. Like, I'm not super skilled with like proofs or theory or like more unusual algorithms and data structures, really, or even some very normal algorithms and data structures. So did this not work? Or was I supposed to return? I think actually after you handle this, you're supposed to return. So that is a software engineering thing to improve, maybe. That's why it didn't work. Okay, one more time. Hello. Okay, look at that. Looks like at least that didn't crash this time. And also, let's look at, check. So our keyboard driver seems to work. I did not write a keyboard driver. I just hooked it up into the interrupt handling, but now it seems to work. I'm in America right now. Why your clock is the same as mine, and I live in Italy. I live in Europe, actually. Yeah. Yeah, so that's why. Yeah. Cool username, by the way. I think that's an Evangelion reference, if I am getting that right. So there's a lot of reversing. Okay, so for Windows kernel exploitation, there's a lot of reversing in the process, making an exploit. It was highly obfuscated, and there's mitigations to bypass. Got you. Cool, nice. Yeah, I mean, honestly, that sounds really difficult to not have the source code for the OS you're trying to exploit, but a lot of people do that. That's cool. Yeah, I feel like that makes Linux sound like easy mode or something, if you just have all the source code. Ugh. Okay, so our keyboard driver is like nominally working, and I can type some lines. Kernel. What code is running? What codeometer? What code is running? That type a line. Who says that? Test keyboard.c. I see. Interesting. And it reads from standard input or something. Or no, that's standard output. Read line automatically reads from standard input, I guess. So, seems like that worked. Open console. But yes, I did grow up in the US. Yep. Okay, so that was easy. But I want to see what this looks like though. Yeah, what does the serial interrupt function do? Console.c, if serial exists. So this runs on every single interrupt. What is serial proc data? Process data, maybe? So I don't, I have no idea what this does. In the com1 plus, so this is like some base address or something, and then you have some offsets from this, and maybe you can read a byte from the serial port using this, using the read. Don't interrupt my lucky charms. Don't interrupt my lucky charms, indeed. Okay. So you can read from the serial port and read, I don't know, a byte or something like this. And then what is it called? Console interrupt. Oh, this is a, all right, this is a wait, whoa, okay, no, never mind. Serial interrupt. Serial interrupt. Okay, so this is a function pointer and it returns an int. And then console interrupt is this thing that takes a function pointer and calls it repeatedly to fill a buffer. And it's like this global ring buffer, basically. Again, I am very curious at how this is all thread safe. If it's just global data that multiple, I guess CPUs are using at the same time. But yeah, so we just read data C and put it into the ring buffer, and then reset the right pointer to the beginning if we hit the end. So that's a pretty simple thing. It's interesting that this is used in both places. So the keyboard interrupt. Ah, I see, okay. The serial port and the keyboard interrupt are both sources where data can come in, but we just have them kind of drain into a common buffer. Yeah, which then the user space part of the, I don't know, of the console code reads from somehow. Open console. And that might even be in shared memory too. No, it's a system call. Console c get. So there is a system call, I see, that reads 1 byte at a time from the buffer, I suppose. Interesting, okay. So, try them both. So I think this is pretty clearly working, I think. Nice. So I will quickly okay. I will quickly commit this code. That wasn't too hard. Refresh. Commit exercise 9, right? Exercise 9. Okay. And then the shell. And that's the last exercise of this lab. Wow. So again, I am not writing like a lot of the code here. A lot of the code is pre-prepared. Okay. I'm going to do this thing that it says, make run icode. Wow. This is the JAWS kernel now with a file system. close spawn new env. Okay. And we are now in a shell. Interesting. Okay. So run your kernel and start user icode execs init, which will set up the console as file descriptors 0 and 1. Now that is interesting. How it does, oh, whoa, did not mean to print. Okay, how does that work? Init.c, no. Init.c in user. Something like this. Okay, so this is the first program that runs in user space. And apparently it needs to create like all the file descriptors. Yeah, on entry, like a user space process doesn't have any files open, kind of, unless it inherits them. And since this is the first process, it's not like the kernel automatically is creating them. Although that's kind of interesting. Maybe it could, but right now, apparently user space needs to do this very grungy work of actually opening the console and duplicating file descriptors. Also new code to me. Wow. This is implemented using virtual memory tricks, of course. Wow. How does this even work? So you give it an old file descriptor, it like looks it up, closes anything that was there, and yeah, they use virtual memory quite a lot in this OS. I think basically the idea is the file descriptors can point to like a page of memory, and to duplicate a file descriptor, basically you make a new file descriptor and make it point at the same like kind of data page that the old one did. Something like that. All right, palm tree break and be right back. Okay, so let's read this again. So this will run your kernel and start this, which will set up the console as file descriptors 0 and 1 input and output. It will then spawn sh, the shell. You should be able to run the following commands. Let me, hello world, piped to cat. That worked. It's very verbose. That's cool that pipes work. So here we have two processes, an echo process and a cat process. And the shell parses this and creates two children and configures the file descriptors appropriately. So the output of this one goes into the input of that one. But it has been a minute since I've thought about how this works. But anyway, we can look into that in a minute, but it seems like that is working. Cool. Cat lorem. That So that's an actual file. Interesting. This is cool. So we actually have a file system we can look through with some files on it, such as message of the day, new. There's no tab completion, obviously. Can't open file or block. Cat new. Oops. New message of the day. Also, I think backspace doesn't work. This is the new message of the day. Yeah, look at all these files on the file system. That's cool. What about this? Num. Okay. LSFD. Interesting. Nice. Okay. Yo, Omar, what is up? I'm a noob, but I'm really interested in. Can someone give me a little bit of context what we are doing here? Totally. Yeah, great to have you here. Here's what I'm doing. I am working on a bit of coursework. Here's a link. So there's this class that MIT had for operating systems. This is actually, wait, the link? Interesting. So, okay, I don't know. I am following the 2018 version of this course, which back when it was known as 828. And it's this OS course from MIT. And I'm doing all of the class projects with it. So it gives you a skeleton OS, and then it gives you some projects to complete. And these are usually like functions to implement and stuff like this. So that's what I've been doing. That's like a super high level overview of what I do on my stream. I've been doing this for a year now. And I've gotten through a lot of the labs. I've gotten through 1, 2, 3, 4. And now we're doing lab 5, which is about the file system and like adding support for a file system, executing programs off of the file system, and having a shell. So that's like a bit more specifically what I'm doing, but in general, I just like in my stream, I just do a bit of casual operating system development for fun and try to learn a few things every time, and to make my way through this course. And when I'm done, I'm gonna start on my own operating system once I have finished the course. Note that so hope that helps provide a bit of context. Note that the user library routine cprintf prints straight to console without using the file descriptor code. This is great for debugging, but not for piping into other programs. cprintf. How libprint. Oh wow. printf.c cprintf. What's up Lotte? How are you doing? So vcprintf, and this calls cputs, right? Which directly goes to the console. What's the alternative? The alternative is writing to a file descriptor, I suppose, using using what? So actually I've not really looked at this code very much before. So for example, printf, like normal printf, what system call does this use? Or does everything use, what about read line? Don't you have that I use Vim, by the way, title? Wait, what do you, I have no idea what you mean by that. Don't you have the I use Vim, by the way, title? What title are you talking? I'm so confused. Okay, so cprintf goes straight to the console. I know what Vim is, but I don't get the joke. Don't you have that? I use Vim is a text editor. Yeah, I'm a fan of Vim. I do not get the joke though. Okay. To print output to a particular file descriptor, use f. Okay, where's fprintf? Do we even have this? Okay. Leave it. Okay, I will leave the joke. fprintf. So what I'm doing right now is I'm just learning a little bit more about how like input and output works in my OS. fprintf, here we go. Wait a sec. So because what's up, Tech Weave? Hello from Tunisia, North Africa. Good content. Thank you for joining. Good to have you, Tech Weave. Yeah, perfect. The joke is that us Vim users constantly pester people for using Vim and tell them how good we have it, not having to run Electron and having everything else on keyboard controls. Right, I'm familiar with that part. Yeah, no, I mean, so are you like trolling me right now? Are you like, I just don't get that title thing you said. Because I use Vim sometimes on the stream, but mostly I'm using VS Code with the Vim key bindings though. Like, check it out. I'm using Vim key bindings and I can prove it. I'm going to jump directly to, I don't know, where can I jump to? I'll jump directly to this TF in one movement. So that proves I'm using Vim key bindings. So, and where should I jump to next? I'll jump to the DX. There, one key movement. So I am using Vim, but just in VS Code. So how does I/O work in the OS? Because they're talking about, like, the coursework is talking about how there's this function called cprintf, which prints straight to the console and doesn't use the file descriptor code. We spent all this time trying to get files working and file descriptors working, but this kind of like printing function didn't use any of that because I guess it didn't work. Printing straight to the console means it was using a system call, like directly using a system call to access like the console device. But what's the alternative to using a system call to the device? The alternative is what we will see right now. I'm discovering this right now. It's using the normal write. Okay. So we actually have normal read and write system calls, I guess. These are library calls, but, oh, wait a sec, what? But it calls cprintf under the hood. So maybe it's not implemented. Is that the point here? This is a great. LSFD. fprintf. FD, right? Oh, I see. Okay. And it's sort of hard to read here. But so there are some code paths here where we are falling back onto the console, but it's only for debugging. In general, the main flow of this function goes and hits this, which is calling into like the file descriptor interface. And that's where we will see, for example, how, here we go. I will get to the Vim question after I look into this. So dev write. So here is an example of the file descriptor device, the file descriptor like backing device or whatever that backs the console. And this thing I'm going to predict is going to use the system call, the sys cputs system call. What's the alternative? Dev file, right? So files are another type, but writing to files is not going to use syscputs. And also, I guess pipes are a different kind of file. And that's actually kind of interesting. So what is dev file, right? This is going to use the file system IPC layer. Pipes are yet a third kind of file. And what do they do? Pipes actually seem to be using shared memory. So the file descriptor can have some data associated with it. And that's what we're using here, I think. We are actually just using some shared memory that's in user space. So, right, and so this is all behind the scenes of the write library call. So actually we don't have a write system call. Again, we're doing like a microkernel kind of thing. And so actually instead of having a write system call, we have a write library call. And it dispatches in user space for like the handler, which is kind of interesting. Usually this code would be backed by the kernel, but here it's in user space. All right, Vim discussion time. Let's get into this. Genuine question, why not Vim though? Like, if you're familiar with the bindings that you use all the time, why not for day-to-day dev? My question is more, what functionality does VS Code have that we don't have in Vim yet? It's fine if it's just preference, but for most people, it's because some functionality they don't have. By no means asking this for being like Vim is better than VS Code. It's because I want to be better than VS Code, if you know what I mean. That's like a great question. For a very, very long time, I was just using Vim. And I think for me, there's a couple reasons. So maybe reason number one is I just find that VS Code has a lot less setup than Vim. I think you still can configure it, but just out of the box, it just tends to work a bit better, like a bit more easily, with less setup. Like with Vim, you generally are not using plain Vim. You're like adding some plugins you like Fuzzy Finder or Nerd Tree or stuff like this. So I just find that you have to do a bit less configuration with VS Code. So Mark, well, I just joined and the first thing I hear is Vim. I use new Vim, love it. Wasn't expecting the topic. Yeah. I mean, yeah, all programmer groups eventually start discussing text editors at a certain point. The other thing I will just say I like a lot is just like the GUI elements of VS Code. Like, for example, I just did this command to find all the references, like look up all the references of this function. I think you can do this in Vim too. And it might even pop up in this like little window kind of thing. But I think, I don't know, in my opinion, this just looks so much nicer than trying to like draw this GUI in like the terminal or whatever. I can fold stuff. I can, you know, browse around in these peaks, that kind of stuff. So I just think the GUI environment is kind of nice. Also, just, you know, that kind of functionality. And Vim can do that as well. Really? Okay. Then yeah. Then I mean, yeah. I think Vim can do a lot of these things, but I just think having like a native GUI window is quite nice. What else? I don't know. Like there is like the debugger view, which I actually don't show debug. Focus on debug console. Okay, I don't know. I like don't know where my debug view is, but I use this a lot at work. There's like a very nice debugger UI built into VS Code. The nerve, bro. The nerve, bro. Okay, so I mean, yeah, I'm sure Vim has a lot of this stuff. I will say, I think installing extensions is very easy with VS Code. Like trivial, you just click some stuff you like, and you know, if I want to install isort, I can just, I guess I already had it installed. I don't know. Like what's it like? I don't know if there's other good extensions I can install. Like if I get Docker, one click away, for example, I think that's pretty nice. I don't know. Yeah, I think those are a couple things. Yeah, but I will say I never like got so deep into Vim. Damn. All right. Yeah. Telescope is the add-on. Okay. Use what's best for you. That's all that matters. Yeah, true. I mean, yeah. There's room for exploring new tools, but for the moment, yeah, and maybe there's things I'm missing, but I do kind of just like the GUI. Also, the keyboard remapping UI is very nice. And you can, if you want to like search for what key bindings are mapped to, you can just like type it in and it'll show you. That's pretty cool. You can also do like kind of cool things like chords in VS Code, where you like, you know, can double press a key combo. I don't like, can you do that in Vim? Probably, maybe. But yeah. All right, I'm gonna stand up for 15 seconds and be right back to stretch. I encourage you to do the same. All right, I use Vim because I hate my life and I don't touch grass. Valid, totally valid. Do you know JS, Coder's Lo-Fi Station? No, I do not know JavaScript. Smith, how long have you been working with kernel development? I've been doing this for about 1 year. I have been exposed to a bit of kernel stuff before that point, sorry, but mostly like not really doing development. Just like doing a bit of reading the kernel, stuff like that. Bro, how can so people in chat use Vim, not people? Well, I mean, maybe you're convincing me to try out Vim next time, but yeah. You also say VS Code LSP works great out of the box. It's difficult to set up every piece of LSP manually in Vim. I just find it fun for some reasons. Let me see if I can convince you about VS Code in other ways. I don't know. Like, I don't, this thing where you can kind of see like what function you're in off the screen is kind of cool. Yeah, I don't know. Where's that debug view? How show debugger? Extension testing, accounts, makefile testing. That's crazy. I don't know how to access my debugger, but it's kind of nice also. All right. I don't know much about kernel. I use modprobe for loading graphic. That's the closest I've ever worked with the kernel. Yeah, I mean that's a start. Best resources. I got you. Resources. So Coders Lo-Fi Station. I have a website where I just kind of collect some resources. But here are some like books and classes that I've liked. So divide between people who prefer TUI and GUI. It's like question coffee or tea. I use TUIs also. Check this out. Have you guys used LazyGit before? This is like an awesome TUI tool. Although to be fair, I also use a Git GUI, which is over here. But LazyGit is an amazing TUI. It's like the Vim of Git basically. And so I use both. I also use Vim to write my commit messages if that counts. Yeah. Wow, this chat's on fire today. Chat's on fire. Nice one. Are you still a student or graduated? I'm not a student. I've been graduated for a very long time, like about 10 years. Is it really that long? No, not quite. 8 years or so. Yeah. So thank you. LazyGit is awesome. Use it all the time. Location, age. All right, well, let's get back to coding, guys. Let's do some coding. This is fun. All right. Have you seen the kernel documentary EPF unlocking the kernel? No, but it's on my list. I think I've seen that pop up into my feed on YouTube. Okay, note that. This is great for not having to print output to a particular file descriptor. Use fprintf. Printf is short for, okay, lsfd. FD. I keep getting coding live streamers now, ever since I've seen Tokyo Swift, and this is amazing. Yo, Bri, thank you for joining the stream. That's cool. I'm also a fan of Tokyo Swift. I wish I had more time to watch streams. But yeah. Guys, I almost convinced him to use Arch Linux time. Oh man, Arch Linux. Yeah, I mean, yeah, maybe that's next level for me. First is just using Vim. I use Ubuntu quite a bit, but only the server one. I don't use it as a desktop OS. So okay, so back to coding. LSFD is this program, and it is kind of, I hear you the term, just like say, if you want to try it, you'll probably enjoy Lazy Vim. Lazy Vim, man. Do a Tokyo Swift segment where you just speed run. That would be fun. I would be interested in something like that. Yeah. All right, LSFD. Just to quickly understand what this does. I mean, this is like kind of weird actually, but it just goes through all the file descriptors, fstat, and like looks some stuff up. It stats stuff. Interesting. Okay, the shell doesn't support IO redirection. It would be nice to run sh. Actually, I have a question for you people that like watching streams. Like, I guess like, what do you do during the stream? Like, are you like kind of like doing chores around the house? Are you like watching for real, like in real life? Are you like in your bed? Like, I'm like kind of curious because I want to get more into this, and I'm just kind of curious, kind of like what I can do to make it more interesting for you. Like just like do a lot more coding or more Q&A sessions or stuff like that. But all right, good night, Bri. See you later. Kickstart and Vim. Entry from Windows is the best choice. My PC is not powerful from the job using smooth. Nice. All right, cool, Micron. Thanks for the feedback. Some Dal Tadka on the side. Streams are TV channels in modern times. Currently watching you while coding. Nice. I mean, I code for like my day job. I probably code for like 3 to 4 hours a day at my day job, and then there's meetings and stuff. And then on my personal time, it's just 2 hours a week in the stream. Yeah, that's just me. I'm watching, funny enough, configuring NeoVim right now, or work on my notes for my math class once I'm done working on my configuration. Nice. Let's put on background while coding or doing other stuff. Okay, cool. I think Afnan does that. He's a common guy that's in here. I'm like, hey Ariel, how would you recommend this course so far? So I'm a fan. I am a big fan of this course. It's helped me a lot. And I think the reason is that it comes with a lot of good setup out of the box, kind of. I mean, the skeleton OS is quite good. It has a good build system. There are a few different yak shaving things you need to fix to get it like working, but that's a good exercise, and you can let me know if you need help with that. But I'm having a good time. Yeah, so I'm a big fan of this course, personally. The next one I would try out is CS61 from Harvard, which I think might be, like, if I had to start over again, I might consider doing this one instead. But I'm having a pretty good time with this, and it's also, it's, the ideas in the course are not super standard. Like it's a little bit experimental. And so I'm personally learning a lot because they use this microkernel like architecture. So I think you're getting distracted from chat or something. No, it's all good. This is super fun. I've never had a chat this active before, actually. So I'm super stoked that everyone's like in the chat right now. This is like by far the most active chat I've ever had in over a year. So I'm having a super fun time. Like your streams is chill, good voice, thanks a lot. Streamers break down their thinking process as when I'm mostly attentive, or devs reacting to dev stuff. I could do reaction videos. You're doing kernel dev or Java layers upon layers of preference. Yeah, I mean, but that's not only in Java. I work in a C++ code base. I work with like a lot of layers of distractions. Honestly, seems more enjoyable than Java for me. Do kernel? Which kernel? Working on Windows. I am not doing Linux kernel development. I'm doing my own custom kernel development, and I am using my Mac, but I'm compiling it to run in Kimu, which is an emulator. So yeah. All right. Shell doesn't support IO redirection. It'd be nice to run sh less than script instead of having to type all the commands in the script by hand, as you did above, adding IO redirection for less than to user sh.c. I think it's possible to become a Linux kernel contributor following your steps. I think yes. I mean, I think actually the way I'm doing it is not the most direct way to become a Linux kernel contributor. Like I'm starting at a very, very foundational, from the ground up point of view. But I think it will certainly help give you a strong understanding of what a kernel does, which will certainly be useful if you're trying to contribute to the Linux kernel. But for example, I contributed to the Linux kernel a couple of years ago with a very, very small patch that just kind of fixed a very small like error message kind of thing that I saw that was wrong in the kernel. And that didn't require this whole like intensive like foundational OS learning effort that I'm doing. So yes. Yes, Jelly Guy. Yep, here you go. Here's the link. Okay. Add IO redirection. Test implementation by typing sh blah into the shell. Okay, so it basically gives us no details about how to do this. So let's look at sh.c and see if we can figure it out. So here's the shell. Wow. So what do I want to do? I want to add IO redirection. So this, what is script? Is script? Okay, so there's an example script. And what happens, interesting. So what happens if I just do this right now? Right, that's what we're trying to do. Redirection not implemented, interesting. That's an interesting hint. So they already have a little bit of an entry point for us to start working with. So sh.c is a program, and oops, I exited the kernel by accident. Oh, there's no exit, interesting. So yeah, sh is a program, but actually, wait a sec. We are currently in the shell right now, and so what it means is that we need to support typing like this syntax when you're typing into the shell. So the shell is this program that reads input from standard in usually, and then interprets it and parses it, and then runs the commands and does all it needs to do. What's up, Jake? I am doing a bit of kernel development right now. I am not pen testing anything. I am doing a bit of kernel programming. Technically, this is user space right now. Okay, so this is my first time ever reading this code, and maybe I can try to speed run this thing. Okay. Speed run, add IO redirection, and be able to redirect files in here. That great. Yeah, thanks for joining. Okay, so basically what happens here, the program reads input that is typed in via this read line thing and gets a buffer of data somehow. And we lightly interpret it. We check if it's a comment. There are some other flags. And yes. And then basically we take the buffer and we run the command, right? Wait, we fork? Okay. We basically have this buffer, we fork, which is kind of interesting. And then the child runs the command and the parent, the shell process, waits. So let's take a look at run command. So here we see parse a shell command from string and execute it. Do not return until the shell command is finished. How do you get access to MIT lab assignments? You just go to the URL. Yeah, it's like public, so it doesn't, there's no login or something like that. Anyone can do it. How many lines? This has like 300 lines? 323 lines. Yeah. Yeah, anyone can do it. I would encourage you to try. I work in the music technology industry. I work on like a musical instrument. Okay, so what are we doing here? So C, not C++, because the course comes with this skeleton OS that is like written in C. So yeah. No, you don't need to sign up with MIT. I'm not affiliated with MIT in any way at all. I'm just a random person on the internet that went to a website and am just like following the coursework. So there's no connection there. I just go to this website every week and I just like read what it tells me to do. The crazy C code, get token. Wow. Okay. Okay. This is. Do not do this at home. This is not good C code, y'all. This is crazy hacker style C code with go-tos everywhere. And this, earlier we were talking about when it's appropriate to use go-tos. I would consider this starting to get out of the acceptable ways to use go-tos. And probably functions are what we should use. But anyway, so they helpfully give us a kind of like a entry point to implementing this feature. Grab file name from the argument list, get token, blah, it's not equal to W. What? Open T for reading as file descriptor 0. Okay. Man, chat's on fire today. Crazy. Yo, we are breaking records right now. No, straight up, we have 69 people in the chat right now. This is crazy. 69 people in the chat right now. I think I've never had more than 20 people in the chat or something like that. This is wild. I wish I could show you a screenshot. I'm gonna take a screenshot right now of my YouTube. How can I? Oops. Preview. All right, this is my proof that we have 69 concurrent viewers in the chat right now. Dang. All right, chat's blowing up. Why is it not good C code? It's from MIT. I mean, just because it's from MIT doesn't mean it's great. I mean, this C code was written by probably assistants, teaching assistants for the lab. Yeah, so I think it could be improved probably. Pretty cool to see. Artus back in college using bare metal gum sticks board, crazy. Low-key goes are good if he wasn't for Zig. All right. Which website are you talking about? Sorry, just arrived. Damn, I think the algorithm is blowing me up right now. This is crazy. I've never had. Yeah, check out this graph. This is fun. Wow. This is the viewer graph right now. It's like this YouTube. I'm curious how. Wait, everyone in the chat right now. How are you finding this stream right now? Is it appearing in your YouTube recommendation or something? I am super curious about that. Hey from Romania. Hey, what's up, Andre? Hey from Romania. Let's go. Which website are you talking about? Moses. I am talking about. I don't know what I was talking about, but I think it's this course website, which I'll post. How many mirrors do you develop in C? A while, but more seriously, this year I've been doing this OS stuff in C. But yeah, I've been doing C++ for 4 or 5 years now. Yeah. Damn, chat's on fire. Front page, recommended. Okay, cool. Recommendations. He was recommending. That's cool. I don't think I've ever been like really recommended this much at all before. Bro, just chilling. Use recommendations. Maybe you should pin the website. How do I pin a website? I was watching Kernel Dome by some Russian girl and then suggested this. For good program streaming, I always tried. 4 years nice. You are a dragon now. Dragon. Yo, we are. Can I pin it as a message? Pin message. There we go. Hopefully that worked. Thanks for the advice. Icon is subscribed, so you got it directly into the feed. Yeah. Okay. Come on, back to development. I agree. We got to get back to coding. So, open T for reading on file descriptor 0. What is T? Token. So open the file as fd. But then what? What is mode? Oops. Who are the other callers of this? Read only, I see, okay. So I'm gonna open T, read only, and fd. Then we can check whether fd is 0. If not, dupe fd onto. Okay, I'm glad they spelled this out because t equals 0. Ft is not equal to 0. Dupe ft onto 0. Let's dupe old new, then close. I'm honestly kind of like confused. I can read this comment and follow it, but wait a sec. Open T for reading. I see. Okay, so basically what's happening here. So we have a shell. Our goal is to allow this kind of thing, like ignore this sh thing actually. Our goal is to allow the shell to support redirection where you can have any command and then you can use this thing and pass in a file. And the command, instead of getting stood in, will get the contents of the file. The way we achieve this is by setting the standard in file descriptor to kind of be fed from the actual file rather than standard in. I mean, also this is like super basic stuff. This is not even kernel development. This is like very, very basic Linux like programming basically. But that's the idea. So we take this file and we open it and get a file descriptor. It's almost certainly not going to be sorry, it's almost certainly not going to be 0. So if it's not 0, we want to force it to be 0 basically. And I guess we use the dupe function to that. Closes any previously open file descriptor at fdnum. So that's the key thing. So using this dupe function, we can take a file descriptor and kind of copy it into a different file descriptor number and like overwrite other file descriptors too. And so we can overwrite the 0 file descriptor like this. So I actually yeah, I think actually that's it. So I am just going to run this. Okay, that was, I don't know what just happened. That was like some very weird output. But it said shell ran correctly. Running sh-x test shell cat. Test shell.c. How old are you? I'm in my early 30s. I'll say that. Yeah, interesting. Test shell.sh. So this is our script. Do you use a mechanical keyboard? Actually, no. This is Kinesis Freestyle 2, which is not mechanical. It's like a somewhat normal keyboard. Yeah. Nice. Crazy. Yo, this chat's on fire today. This is exciting. I'm so motivated to keep going. Anyway, so that was pretty easy. That was actually not that hard. So that was just implementing this. Okay, exercise 10, the shell IO redirection. Aren't normal keyboards mechanical while Gen X here? I'll have someone else explain that to you. I have I've never owned a mechanical keyboard in my life. But I think some people will tell you that mechanical keyboards have like switches and stuff like this, and they feel nice. Yeah. Yeah. What's up, Froggy King? Hi, bro. How you doing? I'm good. I only use Visual Studio. Is this Vim? I mostly use Visual Studio Code. Also, Pacvan. Sounds awesome. Okay, challenge. Add more features to the shell. Your code should pass all tests at this point. As usual, you can, okay, this is gonna be a moment of truth, y'all. This is gonna be a moment of truth. I'm going to, oh wow. Did I forget to run some tests? I could have sworn, make great, all right. Appreciate that, Jake. Thank you. Yeah, if you wanna like the video, that would be awesome. And yeah, if you are into this kind of content, like low level programming, feel free to subscribe. I am doing this every single week for over a year now, and I just kind of just do a bit of kernel development and low level programming every week. 69 likes, nice. All right. Blessed by the algorithm. Yeah, for real. This is crazy. This has never happened to me before, but I am getting blessed by the algorithm right now. Okay, so what I'm doing is I'm uncommenting all the tests for this part of the OS lab. And I'm gonna run them. We'll see what happens. Moment of truth. It might be there's some failures. Yeah, there might be some failures. But I'm passing a lot of the tests. Which is pretty cool. Yo, this is going great. This is going awesome. Haven't failed the test yet. It's passing all the tests. That's also one of the really big advantages of using this kind of coursework for doing your learning, is the coursework comes with a lot of tests. If I was writing my OS by myself, I would need to write my own unit tests, which is kind of boring and not super fun. So it's pretty cool that they just have these tests, and I'm passing all of them. This is sick. All right. What's up, Fenyo? Dang, stuff is on my way to the shower. Can't wait to watch this when it's uploaded. Do you know why a kernel is called the kernel? Actually, not really. It's just kind of like the core or something like that, but I don't know. But anyway, I'm gonna call that a huge win, chat. Every single test is passing, 150 out of 150. I'm gonna save that onto the board, maybe with a bit of a check mark. So that's it. That's lab 5. Oh, so you're developing your own OS? Yes, Wilson, exactly. That's what I'm doing. I'm developing my own operating system. I mean, technically, it's the operating system that came with this coursework, but it's not Linux, for example. It's like a custom operating system. Yep, Sia 92 Yoji. Hey, good morning, Plek. Is that book free? Yes, it's free. It's also linked. Damn, the algorithm is going crazy. This is fun. So what should we do now? I have a bit more time. Man, this is awesome. I would love to just do a longer stream. Yeah, this is like 5 times as many people as I've ever had in a stream. I think what I could maybe do is one of these challenge exercises. Actually, technically, in order to really do the coursework, it says you need to do at least 1 challenge problem. So, what's up, Ronald Gibson? Yeah, never seen the 25 one of your streams. This is awesome. Well, thanks for joining the streams, Ronald. Appreciate that. Let's do a challenge. Maybe you're not sleeping today. Okay. So let's find a good challenge to do. Implement interrupt-driven IDE disk access with or without DMA. You can decide whether to move the device driver into the kernel, keep it in user space along with the file system, or move it into a separate environment of its own. That sounds hardcore. Joking. So huge wins today, hell yeah. Hey, Icron. Yeah. Thanks, Icron. Yeah, I know you've been into a couple of them, so I appreciate that. This sounds like kind of hardcore. I think I would need a bit more time than I currently have for this. The block cache has no eviction policy. Once a block gets faulted in, it never gets removed and will remain in memory forevermore. Add eviction to the buffer cache. Using the PTEA access bits in the page tables, which the hardware sets on any access to a page, you can track approximate usage of disk blocks without the need to modify every place in the code. Be careful with dirty blocks. Interesting. Interesting. What kind of kernel are you working on? DJ Jackson, I am working on, it's this OS that comes with this coursework that I'm following, and it's sort of like this Unix inspired kernel. It's a little bit similar to XV6, but kind of different, and also uses a bit more of an experimental, like microkernel kind of design. Wow, okay. So how would this work, the block? So basically, when we read from disk, we save, like, things get read first into the block cache. And then they stay there. That happens bc.c. It happens right here. So here's where we get page faults into the like disk region of memory, and we allocate the page in the disk cache, and then we read from disk. That's where we do it. Micro with modules. There's no kernel modules, but it's like a microkernel, which just means a lot of things are moved out of the kernel and into user space. For example, the file system in this OS lives in user space. Like the file system driver basically is a user space program in this OS. Also, the fork system call is a user space, is implemented in user space. So basically we read stuff into the block cache, but it never gets evicted. So technically what we could do is every so often we scan through the block cache and look for access to bits in the page tables. What kind of bits are we talking about? It's E flags. So we have an access bit. On any access to a page, you can track approximate usage of disk blocks. So I'm trying to exactly understand what they're like kind of hinting at. I guess, well, first off, if we are loading in a block from disk, we're doing that because somebody wanted it. So basically all of the things in the block cache will have the accessed bit set. So I think what we need to do is, I don't know, like every so often, maybe we clear out all the accessed bits, and then a little bit later we can see if we can go back and recheck and just see if any of these blocks are still not accessed, and then we can evict them. I guess that is... Let's just look at some of these other challenges. File system is likely to get corrupted if it's interrupted in the middle of an operation on crash or reboot. Implement soft updates or journaling. That also sounds kind of complicated. Challenge, implement Unix style exec. Challenge, implement mmap style memory map files and modify spawn to map pages directly from the ELF image when possible. All right, give me 1 second, I'll be right back. So that could be doable. Challenge, add more features to the shell. Backgrounding commands, multiple commands per line. Back, just checking the chat. Hey Aki, thanks for the comment. Very chill and comfy stream. Martin, desk setup, screen accessories, what's your favorite things? Oh, thanks for asking. Yeah, I have like microphone, some Yamaha studio monitors for producing music, Kinesis Freestyle 2 keyboard, some Kirby plushies, and this is like some Dell monitor. Yeah. Shell 1 should be pretty simple. Yeah, I'm trying to see what I should do because I have to leave in a little bit, but this chat's blowing up. Or I could even go. I could look forward at lab 6. That could be kind of interesting. Ah, wait. Okay, am I reaching the end of this? Default final. This is the default final project you can do on your own. Now that you have a file system, no self-respecting OS should go without a network stack. In this lab, you're going to write a driver for a network interface card. That's pretty hardcore. Okay. So this is the default final project. I guess there are other final projects. Work on your own and do lab 6, including one challenge exercise. Otherwise, work on another project. Wow, so I'm like reaching the end of the course actually. And so there's some ideas. So yeah. So hey David, it's pinned. Yeah, it's pinned. How standard compliant should you be? Push tag. Good question. I am not interested in any kind of standards compliance. I am not interested in being a POSIX OS or like anything like that. I'm interested in doing my own like weird stuff basically, which is yet to be determined. So I was hoping that after I do this course, I'll have enough of a foundation to actually do a bit more interesting and fun, like OS research or something like that. Okay, well, that's cool. So I'm reaching the end of the course. There's like a file system, which is the next, or no, the network stack, which is the next thing. I didn't really see anything that was that exciting, actually. Maybe this one. Implement mmap style memory map files and modify spawn to map pages directly from the ELF image when possible. What does this mean? So right now we don't have any kind of mmap. Ah, I see, okay. So currently, the only way to access a file in the OS is to use the file system server, basically. Let me quit this. So right, for example. So here is where we do file stuff. And if you want to read a file, you need to use, it ends up using this backend for like this, like backend for the file descriptor, which talks to the file system server using file system IPC. This makes a lot of copies of the data. Well, also it requires, yeah, you like allocate a buffer, then read the file into that buffer. So the idea would be to add like an mmap system call. And the difference is that it would be like directly, I'm just going to maybe sketch this out a little bit. So right now, I can do a read system call, which requires like a buffer in user space, and the kernel separation is here. It's like the kernel is over here. And so what happens is the kernel has like the block cache, and like the disk is even below here, right? So the disk is here, and the disk contains some data. And the disk and that data, it's stored in the block cache, and then copied into user buffer. So the data exists twice. And then let's say we wanted to do mmap. Maybe an easier way to illustrate this is with like some memory diagrams. So this is like the, okay. So here's a process memory, and we can have one, it's like the user buffer, and the data gets copied from the block cache into the user buffer. So it appears twice. The other option is an mmapped buffer, and this actually points at the block cache. And so the data only exists once there, actually. So, and what would this look like to implement this? I would need to add a mmap. This is called, at least doing this the traditional style. I would add an mmap system call, which it allows you to pass in a pointer, usually, like for an address to put the mapping at. You need to pass it a file descriptor, and length like it takes a length usually. Let's quick look up man mmap. This like could be doable, maybe. Maybe even doable from user space. But it takes an address. That length, that's weird, okay. Length. Protection flag. Yeah, like some other flags. I felt the descriptor and offset. So that's basically kind of what it would look like. And maybe I can just slightly begin to sketch this out. How do I do that? I need to find, like, I would want to make my own little user space program. Maybe I could just repurpose an existing one. So let's just say I'm going to repurpose one of these. So the goal, right. You know what, this might not be that hard. This question is, where do I put this? It's going to go in a lib somewhere. Also, where are all the headers for these things? Like, is there an ipc.h? No. Printf. All right, I am just going to sketch some stuff out in map.c. Map adder. And what if I just do something kind of dumb? And fd. I'm just gonna make the worst version of mmap possible. You pass address where the mapping should be. Hey, sorry, the chat's blowing up right now. How much time? All right. Nerdvana NC. I'm using Kinesis Freestyle too. Priyansh, I was reading your decision or infosec. Any advice for someone who's trying to get into infosec? Advice for getting into infosec would be to study at Pone College to get your technical skills up, and then also try to meet people on the internet that are into that kind of thing too. How much time do you take writing code and thinking what to write? I take a lot of time. I'm very slow. Yes. So Kingspell, no, this is not about buffer overflow. This is just kernel development. So in my awful version of mmap, I'm just going to sketch out what this is going to look like. I'm not sure I'll have time to really implement this. But a user space process will be able to do something like my file to read only, get a file descriptor, and it'll be able to just, const, void my map, and this will be, actually, let's just say it's null, actually. In a lot of the cases with mmap, you don't even pass in an address. You just pass in null and have it choose one for you. And so all I want to do is just pass in basically like the file descriptor, and this is just going to map the file into my address space. Actually, I'm not even going to support passing in that thing. I'm just going to simply say, pass me a file descriptor, and I will do my best to map that in. And I have a couple, like include, like I'll need to, so I can use sys page map to map it into the address space. Alright, I think I am getting in a bit above my head because I don't actually understand all this file descriptor stuff super well yet. So, like, what FD lookup? And what do you get with a struct FD? Device ID. Server files. Yo, thanks Wilson. See you next time. Bobster. Use one project to boost up like in low-level, mid-level projects. There's like this blog post called like computer programming projects every programmer should, yeah, challenging projects every programmer should try. Bobster, maybe this is what you're looking for. So I can, okay, how I want to, so yeah, I'm not really going to be writing super production code right now, but FD lookup, FD struct FD, something like this. Struct, that's off file desk, right? So I can look up I can look up the file descriptor, and then that gives me access to a couple things. But what I want to do, like maybe this actually needs to be implemented in the kernel. I need to get access to the block cache. So maybe this would be like in the file system server or something like that. Where was that diagram? So maybe a regular environment could ask the file system server for the address of an entry in the block cache. And then once it knows the address, it can map it in the process. Yeah, or something like that. Yeah, all of this is like a bit more effort than I have time for right now, but let me kind of slowly bring the stream to a close. Yeah, So yeah, thanks for being here. So I finished lab 5, and I guess next time I will start. I have some options. I could start on lab 6, which is the network driver. I could also start doing my own stuff at this point. I think I'm reasonably comfortable to actually stop doing the course and start building my own OS. Maybe I could do that. Sorry for all the side questions, but we would have the mouse too before we move on to the rest of your house. I'm using an Anker ergonomic mouse. Thanks for the question, Martin. Yeah, wow, this is very interesting. I feel a little bit like I wish I had some better programming to show all of you right now, but yeah, I've been just like doing this course like for over a year, and now I'm kind of at the end, closing in on the end of it. Yeah, this mmap thing would be kind of interesting. I'm still not really skilled enough, I think. Yeah. And it's a bit much to be doing it on the spot on stream. What you because what you can do with the file descriptor is you can get some other stuff. But then who is using this device ID, for example? Yeah. All right, y'all. I have had an absolute blast. Unfortunately, I need to go, but I'm so grateful that everyone is in the stream right now. This is incredible. I've never had a stream with so many people in it. I do this every single week at this time, from like 10 a.m. Eastern time till noon or so. So thank you very much for being here, and thank you very much for subscribing. I'm streaming kernel development every week, and if you want, you can join the Discord too. We can keep in touch. But yes, I am super excited. This is awesome. It looks like the algorithm kind of noticed. So yeah, I'm gonna be back next week, and I will see you then. So have a great week, everyone, and I'll see you next time. Peace. Yeah, thanks a lot. Cheers.